Let me know when you see a blue screen. Still not showing? Yes. Can you hear me? You sure? Hello? It should work, yeah. Is your speaker... Oh, does it say still please stand by? Oh, okay. Yeah, and there's like a 10-second delay between when I speak and when you hear. Oh, it's coming now. Does the audio sound good? It's okay. All right. Sounds good. All right. Excellent. All right. Thanks, Arca.
Are you kidding? You're using a phone. Yeah. Now they're like, we have the school. I got advice from school. Yeah. Welcome to so, yes. project or PDFs.
That's correct.
You're not really started as much as you use. The plan is to advise them to use presentation about 20 minutes clarification type of questions, clarifications, and detailed discussion type of questions. Is requested to hold it on for the session. So, without further ado,
So thank you everyone for coming. Thank you for that introduction, Dr. Milko. And today I'll be presenting laser-assisted micromilling with minimum quantity lubrication and vortex cooling. And this is just the basic outline. I'll start with a general introduction to micromilling and laser-assisted micromilling. I'll be going into where research is lacking in the problem statement, and then I'll be stating our research objectives of how to meet those where research is lacking. And the rest of the presentation will go into the approach and the experimental methods and the results, and we'll finish off with conclusions and future work that would be possible. So to give a basic introduction, because technology has continued to miniaturize in the last few decades, manufacturing processes that can create micro and mesoscale features are needed. In some places where that is necessary is in the aerospace or the medical or the electronics industry, and I've just given a few examples as shown above. One process that's commonly used to create micro and meso features is micromilling, and that's because it has high dimensional accuracy. It can create features with low surface roughnesses, and it's usually more economic than alternatives such as EDM or ECM. And just to give example of micromilling, here's a medical implant, and these features were machined with 0.2 and a 0.4 diameter, a millimeter diameter tools. So you can see there it's a very small medical implant. And to give an example of that, I'll be passing around a conventional size end mill, and just below it is a micro sized end mill for comparison. So going into the limitations of micromilling, as you can see, once you get the tool, you'll see that they're very small in diameter. They can go down as far as 40 microns in size. And because of their small diameter, they're very prone to break. And because of this, the tool strengths are very low, and they often wear very rapidly because of the very small cutting edge, which leads to significant plowing and rubbing due to the size effect. And there are several approaches to overcome these limitations as far as tool strength and tool wear. One is just lowering speeds and feeds, which lowers the material removal rate, which is not optimal. Another is introducing tool coatings to help reduce friction and heat to the tool. Some of the other conventional methods we'll be going into is flood cooling, which we will denote as wet. And flood cooling is just, or wet, is when you have a coolant directed onto the end mill, and this helps remove heat from the tool and also lubricates the tool workpiece interface. The next technique is minimum quantity lubrication, or MQL. And what MQL does is it takes atomized oil droplets mixed with air, and it sprays onto the tool workpiece interface, very similar to an aerosol product. And it is shown in a lot of literature that it's better able to penetrate the tool workpiece interface compared to wet cooling, and far better tool wear, or reduced tool wear. Another technique is vortex cooling, which takes compressed air, and due to the Rank-Hilsch effect, it can output very cold air temperatures onto the tool to help reduce wear. And then the last technique is a hybrid process called laser-assisted micromilling. And to give an introduction to laser-assisted micromilling, the basic concept is you have a very small end mill, removing material as shown, but simultaneously you have a laser pointed directly in front of the end mill, And this laser preheats the material, allowing it to shear at lower forces. And this thermal softening effect uh, greatly reduces wear because of the reduced cutting forces. And it's very well suited for difficult cut alloys. And just to give an example of some prior research done on laser-assisted micromilling, this shows the resultant cutting forces and the number of grooves cut. As can be seen in a dry cutting condition without lasers, the cutting forces are very high. And it was seen that after cutting 4 grooves that the tool broke. Under the exact same cutting conditions with the same feeds, speeds, and depths of cut, we can see that the laser greatly reduced forces and allowed the tool to continue far much longer than the dry cutting conditions. This just shows how laser assist can also benefit the tool. As is shown in the dry case, there's significant chipping of the tool, but under the exact same cutting conditions, you can see that the tool is better preserved, and there's no chipping and there's negligible rounding. In another study, in the cutting of Inconel, it was shown that in the dry case, there's significant flank wear, but with laser assist included, there is significantly less flank wear. And more thorough literature review is shown in my thesis, but where research is lacking is laser assist is often presented as a technique that can replace conventional techniques, such as flood cooling or M2L or vortex, but there is no systematic comparison comparing LAM to wet M2L or vortex cooling methods. Another place where research is lacking is there's no studies aimed at enhancing the tool life by including M2L or vortex cooling to the LAM process. So to meet where research is lacking, we've come up with these research objectives. The first is to compare the micromachinability of a difficult to cut alloy. And for this research, we've chosen A286 steel. And we'll be studying its micromachinability under dry, wet, and LAM to have a systematic comparison. The next objective is to understand the tool wear behavior in LAM and its effect on micromachinability over a prolonged period of cutting. And the last objective is to characterize the impact of M2L and vortex cooling on the micromachinability and tool wear. So to meet these 3 research objectives, we've come up with 3 experiments. The first is to conduct tests machining A286 under dry, wet, and LAM cutting conditions. The second experiment is to conduct a tool life test under LAM for a prolonged period of machining. And the last experiment is to conduct a LAM test with M2L and vortex cooling involved. And to give an example of our experimental setup, there's a lot of elements and a lot of equipment involved, but I'll just be going over the main elements. One of the main elements is the spindle. It's a Nakanishi spindle that's capable of reaching 60,000 RPMs. The end mill that's being passed around is positioned in the spindle here. And the workpiece is mounted to several elements which are driven by an X, Y, and Z stages to dictate the tool path. While that's ongoing, we have a ytterbium fiber laser that directs a laser directly in front of the tool cutting path. And then for the wet experiments, we have a pipette that allows the flow of coolant to the tool during our experiments as well. And as part of the approach, the workpiece that we chose is A286. It is very commonly used in the aerospace industry because of its very high tensile strengths, and it has great corrosion resistance as shown by the oxidation temperature. Even though it's a very attractive metal to use for engineering applications, it is very difficult to cut due to its very high nickel content, which leads to significant work hardening of the material during the cutting process, as well as low thermal diffusivity, which leads to excessive heating of the tool. It's also known to have many abrasive carbides in it after it's been heat treated, which create a lot of abrasive wear on the tool and tool coatings. And the tool we'll be using in the experiment is a 0.5 millimeter diameter end mill that is smaller than the diameter of the lead in your mechanical pencils, just to give you context. I'll be passing that around as well. Feel free to open up the bag. There's a magnifying glass. Help you see the features. So in the next slide, we'll be showing a video of the design of the experiment. And just to restate the objective, it is to compare the micromachinability of a difficult to cut alloy, and then for this example, we chose A286 under dry, wet, and lamb cutting conditions. To do so, we did it under dry, wet, and 2 different lamb conditions. These parameters were chosen off a thermal mechanical model, and these 4 assist methods were tested over 8 different cutting conditions with varied cutting speed, feed, and depth of cut. And these cutting conditions were chosen from a literature review of micromilling of similar high nickel content alloys. And this shows an example of a test. As can be seen, here's the micro end mills rotating, and it's moving material as oil helps lubricate the tool during the cutting process. And that's actually the same part that is being passed around right now. And you can be seeing there's a very small groove here, and in this test we see a laser is directed directly in front of the tool and thermally softens the material as the end mill removes material very rapidly. Okay. So to show how cutting conditions affected the micromachinability of the workpiece, we decided to show all 8 cutting conditions for the dry test. And I know this is a lot to take in at once, but as you can see, there's cutting speeds, different feeds, and different depths of cut for these 8 cutting conditions. And the one big takeaway here is that for the experiments with high depths of cut, which are 2, 6, 4, and 8, we can see that there's more burr, as shown here, and chip adhesion shown by these little black specks on the workpiece. And the same is seen in 4 and 8. And then to further compare the micromachinability of the different assist mechanisms, we can see that dry had significant burr, as is shown, and that's expected because there's nothing helping the cutting condition. And we all can see significant burnishing on the surface as long as a lot of chip adhesion by these little black specks. In the wet condition, with the addition of lubricant to the workpiece, that oil helped flush away a lot of the chip adhesion and also helped reduce burr, as is shown, and led to a less burnished surface, as shown. Interestingly, with the addition of laser assist, we can see that due to the thermal softening effect, the groove looks pretty good or pretty clean and with less chip adhesion, and also that there's less burr than there is in the wet case. And then, interestingly, with lamb 18 watt, that also led to a groove with less chip adhesion than in the dry case. However, because the laser at 18 watts is at a higher laser power, it led to higher temperatures of the workpiece and more thermal softening, which allowed it to be more ductile and led to more burr formation than the wet or the lamb 12 watt case. However, it did better than the dry. And then this illustrates how the groove depth was affected by the different assist mechanisms. And as shown, we have the target depth of cut, which is programmed for the experiment. And I'll just go through for each condition. As you can see, the dry tended to undercut the target depth of cut. And that's because of, one, tool wear, and also due to the elasticity of the workpiece, which as the cutting forces press down on the workpiece as well, in the Z component, it would push the workpiece away, leading to a lower depth of cut. However, with the addition of wet, we can see that marginally improved and led to slightly more accurate depth of cut. And interestingly, with the addition of laser assist, we can see that that was actually the most accurate and the closest to the target depth of cut. However, with the laser assist at 18 watts, due to the increase in the temperature of the workpiece thermally expanded upwards and led to a higher depth of cut than the other cutting conditions. This just shows, moving on from the micromachinability of the workpiece, we moved on to the tool condition, and it's shown by the schematic. We're looking at the flank view here, and that's what these images represent. For the dry cutting condition, it was seen that there was chipping of the tool and excessive flank wear as well. However, with the addition of cutting oil, that helped cool the tool and led to no chipping and also reduced flank wear marginally. Interestingly, with lamp 12 watt, it greatly preserved the cutting edge compared to both the wet and dry seams, and also marginally reduced flank wear as well. And then with lamp at 18 watts, since that was at a higher laser power and the workpiece was at higher temperatures, it was much more likely to adhere to the tool as shown by this large clump of A26, and that's built up edge, which we will further investigate later. To help quantify the amount of tool wear, we measured the diameter of the tools before and after each experiment, and this shows the diameter change of the tool for all 4 assist mechanisms for all 8 cutting conditions. There's a lot to take in, so we'll just be focusing in on one, since most cutting conditions show the same trend. As can be seen, dry tended to lead to the most change in tool diameter, and that's because it had the most wear, as would be expected. With the addition of cutting oil, the wet marginally improved, as shown by the red bar. And interestingly, with the addition of laser assist that led to thermal softening, that greatly reduced the change in tool diameter. And with the laser at a higher power, that allowed for more thermal softening and led to even less change in tool diameter. And I've shown that lamp at 18 watt reduced the wear on the tool by as much as 29% compared to dry and 21% compared to wet. And in a similar fashion, we showed the cutting forces for the first and last group for all cutting conditions under all assist mechanisms. And again, since there's a lot of data to take in, we'll just be focusing in on one. And as can be seen in the dry cutting condition, the last group was seen to have the highest cutting average resulting force. But with the addition of laser assist, the thermal softened the material, we can see that in the 18 watt case that it greatly reduced cutting forces by as much as 50%. So just a recap of the key findings in experiment 1. We saw that lamp greatly improved the groove condition. It led to a more precise depth of cut than wet. Lamp 18 watt greatly reduced the change in tool diameter and led to less flank wear. Compared to the dry case, it led to a 21% improvement, and compared to the wet case, it led to a 29% improvement. However, it did create built-up edge. And cutting forces were also greatly reduced with inclusion of lamp, and it almost reduced by 50% for cutting condition 1. So moving on from experiment 1 only machined a small amount of material, and for experiment 2, just to restate the objective that was introduced earlier, it was to understand the tool wear behavior in lamp and its effect on micromachinability over a prolonged period of cutting. So a single tool life test was drawn at lamp 18 watt under these parameters that are shown. And during this cutting process, we periodically observed the groove quality in terms of groove dimensions and tool wear. And this was done over a cutting period of 25 minutes, or a total machining of material removal of 150 millimeters. So this just shows the groove quality over the tool life test. And I know there's a lot to take in, so I'll just go step by step. The top shows the groove number. The numbers below it is the elapsed amount of material removed and the amount of time that tool has been spent cutting. As can be shown, when the tool is new, it led to very little burr formation, and it had very distinct cutter marks on the bottom of the groove. This just shows a cross-section of the same groove, and it can be seen that when the tool is new, it led to a very square cross-section because the tool had not worn that much yet. But as time progressed, the tool did wear, and more ununiform berm was seen, and that pattern continued. And by the end, we can see that the bottom surface has more of a burnish effect compared to these nice cutter marks that we're seeing on one of the initial grooves. And also, we can see that the groove cross-section tended to round in this process as well. So there's a lot to take in, but really the one big takeaway is the tool wore, burrs formed, the bottom surface burnished, and there was more rounding of the cross-section. Wait, sorry, the second number? This one?
Second rule is
Oh, that represents the amount of time that tool has been machining.
second.
Of that one? That's the elapsed amount of material removal. How much material? Cumulative, yes. And then from those given cross sections, we measured um, the accuracy, and this just shows a side-by-side comparison of the cross sections for the cumulative amount of material that was removed. So this is when the tool has only moved about 7 millimeters cubed, and the green line represents when the tool has already worn some and removed 153 millimeters cubed. And as can be seen, when the tool is new, it led to a very square cross section. And when the tool had machined a significant amount, you can see that the grooves receded inwards by about 7 microns. And also that the tool rounded more at the bottom, as is seen. Moving on from the groove conditions, we observed, again, the tool along the flank view and the bottom edge view, as seen. And we also included a picture of a new tool to give perspective. And as can be seen, the flank wear did occur as more material was machined, and built-up edge was formed as well. And it was seen that as the tool machined more, built-up edge tended to increase as well as the flank wear. So that's the one big takeaway from all of these images, is that flank wear increased and built-up edge formation was prevalent and increased. Also, to help measure tool wear, we also measure the corner radius at different points, as well as the diameter before and after. But since all the wear measurements showed the same trends, we'll be only showing the results for the corner radius. As is shown, we have the corner radius here, and the amount of elapsed or cumulative amount of material that's been removed. And similar to what results that have been shown in previous tool life studies, there's a rapid amount of tool wear in the initial 20 millimeters cubed amount of material that's been removed, and then afterwards it reaches a steady state of wear, which only linearly increases. So just as a recap, the key findings of experiment 2 were the groove quality did marginally decrease as the tool wore, and the grooves had more burr and became more tapered and rounded at the bottom. However, this decrease in groove quality only showed the grooves receded in by 7 microns after cutting 150 millimeters cubed, or 25 minutes of cutting. Tool wear was very rapid initially, but after the first 50 millimeters cubed, it increased gradually thereafter. Built-up edge on tool was very prominent. And because built-up edge was very prominent, that is a bit of a concern, because once built-up edge forms, it will eventually break off, and it often will take some of the tool coating with it, or even chip the tool if permanently damage the tool. So we wanted to investigate whether MQL or vortex cooling could help prevent built-up edge. And so moving on to experiment 3, just to restate the objective of experiment 3 is to characterize how MQL and vortex cooling affect LAM's micromachinability and how it affects tool wear as well. And to do so, we ran the micromill at the same parameters as experiment 2, and we ran the laser parameters the same as experiment 1 and 2. We also included 2 different MQL parameters and 2 different vortex parameters, and these parameters were chosen based off what was seen in the literature review to be beneficial to tool wear. And with these parameters, it led to 10 different test combinations, but due to time, we'll only be showing you the significant experiments, which are the dry and lam, which more or less are the controlled experiments, and lam plus MQL2 and lam plus vortex 2 as shown. And we machined 4 grooves, and we'll be showing you results soon. This just shows a schematic of this experiment. Similar to previous experiments, the laser spot is directed in front of the path of the tool thermally softening material. And in this case, we added a nozzle on the back side of the tool, which, if it was vortex, it would lead to cooling of the tool, and if it was MQL, it would lead to lubrication of the tool. And this just shows a real-life example of this schematic, as we showed. So again, the tool was observed as it was before in previous experiments. As can be seen in the dry case, there's significant wear. However, there's no built-up edge because there's no laser assist causing thermal softening and allowing material to adhere to the tool. In the lamp condition, as seen before, there's a very large amount of built-up edge. There's a large clump of A286 on the front edge of the tool. And interestingly, with the inclusion of MQL, we can see that there is no built-up edge, and there is less wear actually on the tool with the inclusion of MQL to lamp. And this also shows the result for lamp plus Vortex 2. It marginally decreased built-up edge, but not as much as lamp plus MQL2. So the key finding was, with the inclusion of MQL2 to the lamp process, there's no or less built-up edge, and it leads to less tool wear. And this is just a side-by-side comparison of lamp and lamp plus MQL2 of the blank view of the tool. And to help verify what that large clump was, we did an EDS, electron dispersive spectroscopy, and we observed certain elements, and the dots here represent the most dominant element of these factors. So the red dots represent iron, which is the most prevalent element in A286, or the built-up edge. The blue represents the tool substrate, which is tungsten, and green represents titanium, which was the most prevalent element in the tool coating. And as can be seen, there's a significant amount of red or built-up edge on this tool, and there's also significant workpiece adhesion on the flank side of the tool as well. With the inclusion of MQL, it greatly reduced workpiece adhesion and built-up edge, as seen here. And to quantify built-up edge, we measured the percentage weight of specific elements. And shown in shades of red is the elements that are most common in A286, and shown in blue is the elements most prevalent in the tool. And as can be seen under the lamp cutting conditions, there's a significant amount of built-up edge shown by the red bar, and there's less of the tool along the flank side of the tool. With the inclusion of MQL, it greatly reduced built-up edge here, and you can see more of the tool is shown in that EDS analysis. And this just shows the overall comparison. Vortex did reduce built-up edge, but not as much as MQL. To further the tool wear analysis, we again measured the change in tool diameter as shown. It's no surprise that dry had the largest change in tool diameter because there's nothing assisting the cutting mechanism, but with laser assisted greatly reduced tool wear, and with the inclusion of MQL, it did even better than lamp. And then the tool corner radius was also measured, and is shown lamp plus MQL2 again did better than lamp, and lamp plus Vortex 2 did marginally help the corner radius as well. This again shows the groove quality of the dry, the lamp, and the lamp plus MQL and lamp plus Vortex 2. Most of the groups look very similar, though there are some noticeable aspects though. With lamp plus MQL2, we did see more burr as seen by this dark region here. And also with MQL, interestingly, we see a heat affected zone by this gray streak right here. And that's because with the inclusion of MQL oil on the workpiece, it led to more absorption of the laser radiation, and that led to better heat penetration into the workpiece, leaving a heat affected zone. But that is something we've hypothesized, but it is strongly suggested by the literature that that's very possible because oil is known to have more absorptivity than metals. And LAM plus Vortex 2 also was seen to have a heat affected zone, and we believe that's because with vortex cooling, it thermally contracted the workpiece away from the cutting edge, and because of that, more of the thermally softened material, more of the thermally softened material was left behind, and that led to this heat affected zone. And again, we measured the groove depth similar to experiment 1, and as expected, dry undercut the target depth of cut, and LAM overshot the target depth of cut. But interestingly, LAM plus M2L2 increased the depth of cut compared to LAM, and that's again due to the oil allowing more of the laser to be absorbed into the workpiece and allowing the workpiece to reach higher temperatures and thermally expand upward into the tool, leading to a higher depth of cut. Interestingly, with vortex cooling, we saw that due to the cooling effect, it thermally contracted the workpiece downwards, and it also it compensated for the thermal expansion caused by the laser. And we also measured the groove width on the first groove and the last groove, and the difference of that is the change in the groove width that's shown here. And as expected, because the dry experiments had the most tool wear, it had the largest change in the groove width. And with inclusion of LAM, that greatly reduced the groove width. And with inclusion of MQL2 LAM, it also benefited groove dimensional accuracy. As can be seen, there's less of a change in the groove dimensions. LAM plus Vortex led to actually a larger change in groove width. Along with groove dimensions, we also did measure surface roughness. The one interesting result from this is dry actually had the smoothest surface compared to all the other tests, and that's because dry had the most tool wear, and because of the tool wear, it had more of a burnishing effect on the bottom surface, leading to a much smoother surface compared to LAM, LAM plus MQL, and LAM plus Vortex 2, as we've shown. And again, the cutting forces, the average resultant forces were measured on the first and last groove. Similar to experiment 1, dry had very high cutting forces, LAM greatly reduced cutting forces. But with inclusion of MQL2, which helped lubricate the tool, it lowered forces by about 10%. And we believe that's due to decreased friction by the cutting oil and reduced built-up edge. Vortex 2 also did reduce cutting forces by 15% compared to LAM as well. And we did repeat the MQL test to verify, and we saw that these cutting forces results were repeatable, and that 10% decrease was constant. So just to recap of experiment 3, compared to LAM, LAM plus MQL led to more accurate groove widths, and by as much as 41% compared to LAM, because it helped reduce tool wear. However, it did increase the depth of cut due to the increase, as we hypothesized, the increased laser absorptivity caused by the oil. It greatly reduced built-up edge and tool wear, and compared to LAM, it reduced the change in the corner radius by as much as 27% because of reduced wear, and cutting forces were seen to decrease by 10%. Compared to LAM, LAM plus Vortex 2 created narrower and shallower grooves, and that's due to thermal contraction caused by the cooling effect, and forces are lowered by 15%. And this is just the overall conclusions for experiment 1, 2, and 3. LAM was more beneficial than wet assist and greatly reduced tool wear. LAM reduced forces significantly. For cutting condition, cutting condition 1, it was seen to be 50%. LAM is capable of preserving the tool for machining for extended periods of time with only a marginal decrease in groove quality. And MQL2, in the addition of LAM, showed to even further benefit the tool by reducing tool wear and led to better groove accuracy by as much as 41%. MQL2 eliminated built-up edge in the LAM cutting condition, and Vortex coolly marginally reduced built-up edge in LAM. Some places where future work could continue. As we did observe that the laser, we hypothesized that the oil on the top of the workpiece led to increased laser absorptivity of the metal. So that's something that should be further investigated, whether experimentally or using models. Another aspect is that could be investigated is cryogenic cooling has been shown in macro scale turning to greatly reduce tool wear. However, cryogenic cooling is yet to be used in micro machining. One aspect we noticed from vortex cooling is that the vortex cooling did affect the workpiece during the cutting process. So if cryogenic cooling were to be used, it would have to be much more focused on the tool than in our experimental setup. And another place where research could continue is there has been previous work on different tool coatings in laser-assisted micromachining in the past. However, many new coatings have came out in the last 2-3 years. For example, aluminum chrome nitride, which is shown to be even was shown to have properties that are even more beneficial than titanium aluminum nitride as far as surface adhesion to the tool and higher oxidation temperatures. So coatings like that could be further investigated. And I'd like to first acknowledge my very close friend, Alberto. He was my colleague here in Experiment 1, and he was a very great help. This project would have not been possible without the funding of Alcoa. And I'd like to also thank the PMRC, the students, the faculty, and staff, because it's helped me out a lot during my time here. A lot of the fabrication that I did on the micromill would have not been possible without the help of Stephen Sheffield and the many members of the machine shop. Many of the pictures that you saw were taken in the IEN, so I could not been able to get those pictures out without the help and training of IEN faculty or staff. And I'd like to greatly thank Dr. Melko. He's gave me a lot of advice and guidance during this research project. And I'd also like to thank Dr. Liang and Dr. Saldana for taking the time to be at my thesis committee. And I guess it's a good time to stop and ask for questions.